so welcome to another video, and today we're going to learn about circuits. Okay, so this is a lesson or topic in physics. So we're going to learn how electrons flow, making electricity, how batteries are connected or can be connected. Also, what happens when we connect resistors in parallel or series. So basically, circuits is a topic in electrical engineering, and of course I'm going to teach you some basics of the electrical engineering today. So what you were seeing here is simulation from Phet, Phet simulation, and what you can see here is the or a series of resistors connected to a 12 volts uh, 12 volt battery. Okay, so first things first, we have to talk about Ohm's law. But before that Ohm's law, we have to understand that electrons travel from the positive down to the negative terminal of the battery. However, this is quite tricky because some experts believe that it's all the opposite way. So that's why we have conventional. Okay, so we have conventional and we have electrons. When we talk about electrons flow from the anode to the cathode. And the anode is basically the positive one, and the cathode is a negative one. But if we are talking about the conventional way, this is how when we talk about conventional, this is what we really think. Okay, positive to negative. Okay, but um, nonetheless, it's just an idea that how the electricity will flow. But if you ask me, I'm going to focus on electrons flowing because this will help me, or this will guide me, or this will help me know how the electrons will flow or how it really flows. Okay, the reality. Okay, so going back to Ohm's law, so it's actually George Simon's. No, not really George Simon. It's Ohm's law. Okay, we have to ask Google. So it's, who said it? George Simon O. Oh yeah, George Simon O. So he said, okay, so he said that the current that flows through a circuit is directly proportional to its voltage and inversely proportional to its resistance. So what this really means is, sorry, Joe. Okay, so he said that current I is equivalent to voltage divided by R, or resistance. This means that the current is increasing when the voltage is increasing, but the current is decreasing whenever there is a decreasing resistance. Okay. Basically, Ohm's law is limited in a way that we cannot really use it when we talk about superconductors. So when we say superconductors, okay, when we talk about superconductors, these are materials that basically doesn't have any, almost reaches zero resistance. Now, is it possible, Sir Ikal, that we have a material which is zero resistance? Well, theoretically, yes. It's possible, and based on experiments in simulation in labs, they were able to make superconductors. So these are resistors or materials which have very, very small resistance. So let's check using the simulation. What will happen if we have zero resistance? Alright, so let's put some battery here. Actually, it doesn't really matter if it's going this way or the other way. Doesn't really matter. So, okay, so we put a resistor here. Oh, sorry. Okay. So you can see here, if we're going to make a zero resistance here, see, what this really mean is this. When you have a formula, let's say the battery has 9 volts, okay, and we are seeing a resistance which is equivalent to 0, but this is not really real 0, okay, but we can say that this is 0.00000000001, okay, and what will happen if we do that? Basically, you have 9 divided by 0.100. So see, it cannot be divided by 0 here, but if we're going to talk about this one, the current will basically be very, very huge. Okay, so let me help you break that one. So, for example, I is equals 9 divided by 0.1. Okay, so this is equivalent to 90. When I is equivalent to 9, 0.001, basically you have 900. So imagine every time that you are increasing the number of zeros in the decimal places, you're practically making the numerator very large as well. So if you have an almost zero resistance or divisor, you're practically making 9 very big. So that is the reason why the battery here is signified with the flaming one, because it's too much already. It's practically. So that is basically what the I believe the limitation of the Ohm's law. Okay, because this is really true for all cases. Okay. Now, going back to the circuit here, we see that the flow of electrons is like this. You know, it's slow. It's really, really slow. Now, when we talk about resistance in series, we basically add them. Okay? So, when the resistor is in series, we basically add them. So, okay. So going back here, we simply okay, we simply add 3, 6, and 9. So the total resistance, or practically what you're going to do, is you're going to combine them into one element. Okay, so you're making it R total. So that's 9 plus 3 plus 6, and that's 9, 18. So you have 18 ohms. Okay, so this is basically same or similar when we do this. Okay, and you put a wire here. Okay, and then another resistor. So we have calculated that the resistance is 18 ohms, right? So let's try 18 ohms. Okay, and let's compare if they move the same. Well, if you ask me, they move exactly or behave or they have the same speed. If you ask me. Okay, so that's it. Right, so we're going to, again, you're going to combine the resistors because they are connected in series. But how about if they are connected in parallel? Alright, so let's change this to 12 volts. So if you can see, this circuit moves, the electrons flowing in this circuit is slow, pretty slow. But if you connect them in parallel, it changes. Why? Why does it change? Well, I have to tell you first that electrons move when there is a low path resistance. So when I say, if you're going back to the Ohm's law here, again, the current is basically telling you how much electrons flow in a circuit. So basically, a current is charge per second. Okay, so coulombs. I don't know if you remember that one, but current or amperes is equivalent to coulombs per second. And we all know that coulombs is basically saying how many electrons flowing per second. Okay? So, electrons have a charge, remember? So, electrons have a charge. We all know that. So that's equivalent to, you search that one. So practically one electron has a charge. And when you talk about huge number of electrons, okay, so you can combine it into coulombs, and that how many electrons are flowing into that circuit in a second is basically what gives you the ampere or the current. Okay. Now, what's the point? I mean, the point here is this: the current or I will be bigger if you have a small resistance. Now, the flow of the electrons in the circuit obviously tells you they're slow. Okay, they're slow moving, which means that resistance is big. Now we have computed that the total resistance of this circuit is 18 ohms. So when we see something which flows like this, obviously the resistance must be low, right? So what's the formula? So whenever we have resistors which are connected in parallel, you practically you basically do this formula. Okay, the resistance total is 1 all over 1 of R1 plus 1 over R2 plus 1 over R3. Okay, so it's kind of looks like this. So you basically do this 1 all over, we have 1/3 plus 1 over 6 plus 1 over 9. Okay, so do that math. Okay, we're going to do the math. Hold on. So okay, so okay, so 1 all over 1/3 plus 1/6 plus 1 over 9. Okay, so this is 11 over 18. 18, so that's 1 times 18 over 11, and this is equivalent to 18 divided by 11, so this is 1.63, but it's continuing. Okay, so 1.6333. Alright, so imagine 1.6. Now, this is what's important. The thing that you're going to see here. Because what we did is basically adding up all these resistors together. So what you see in between of each resistor is not really important, but what's really important is here. Okay? Kasi ginawa nyo na parang isa ito eh. So ito na yun. So basically this is what you see. Okay? So when we connect resistors in parallel, practically you make them smaller. When you connect resistors in series, you make them larger. Okay? So that's it. Now, what will happen if you connect batteries just like resistors? Okay, so when you see batteries connected like this, you also have the same effect. It's like you are combining them. Now, if you're going to use a voltmeter here, okay, so black is black and red is red, so you add them up. So 9 volt plus 9 volts equals 18 volts. Okay, but if you're going to connect them in parallel, if you connect the battery in parallel, you still have the same voltage, like this. 9, see, still the same 9 volts, still the same 9 volts. Right? Now, the question is, what happens when you connect batteries in series and in parallel, but when you talk about the current? Okay, so to do that, you have to use a ammeter. Okay? So, Sir Ikal, how do you use an ammeter? Do you connect ammeter like this, like the voltmeter? No. You connect, the connection or the way that you use voltmeter and ammeter is different. Because current or the ammeter measures the amount of the electrons that flows. Okay? You're going to measure the amount of electrons that flow in the circuit. So basically, what you do is to connect the ammeter like this. Because the ammeter will measure how many current that flows. Whereas the voltmeter doesn't do this. The voltmeter or the voltmeter does not measure the amount of current that flows. That is why you connect it simply like this. Alright? Because if you're going to connect it like this, you will have a different result. Imagine, see, 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 you have a different result. Because the voltmeter doesn't measure the amount of current that flows, but only the magnitude or the speed of the electrons that flows. Okay, so when you see, okay, so let's check. When I said the voltmeter only measures the speed or the speed of the electrons that flow that moving. Okay, so let's check it like this. Okay, so we'll measure the voltage here. So it's 4 volts. Whereas if you okay, not here. We'll check it here. Okay, so 12 volts. Obviously 12 volts. But if you're going to compare these two, okay. Okay, sorry. What? Nangungulit ang point ko. Basically they have the same, really. Yeah, they have the same. I don't see it why. Okay. Yeah, it's the same. So yeah, you don't have to do that. Basically what the okay, I remember my point. So the voltmeter measures the speed of the current that flows, or the speed of the electrons that flows, right? So it's 12 volts here. Now, interestingly, if you're going to check this one out, wow, same voltage, but if we look at this one, 4 volts. Alright. 6 volts. 2 volts? What? Okay, what I did is I measured the voltage across each resistors this way. Across each resistors, and I found out that the voltage across each resistor is different. Whereas if I'm going to do this exactly the same thing here in parallel configuration, they're the same. Well, yes, they're the same, because always remember when we talk about parallel connections, the current, okay, so the current is different across each resistor, but the voltage is same or similar. Okay, whereas in series, the current is similar and the voltage is different. Okay. Actually, you only have to look at how the electrons flow. Okay. We don't really see it here because this is practically small. So we increase the voltage here. No. Okay, we make it 50 volts and then make this 5 ohms. Okay. They're the same, right? But if we're going to do this, now you see what I am talking about. The current is differently, the current flows differently in each resistor when they are connected in parallel. So they're different across each resistor in parallel. But the voltage remains exactly the same. So the flow of electrons across each is the same. It's the same, it's the same. But the current that flows in each resistor in parallel is different. So practically, the higher the resistance, the slower the slower the movement of the smaller the amount of current that flows. So imagine here, in 1 minute you have 1 electron. Here you have 3 electrons, 5 electrons per second. Here you have the 10 electrons per second. So you have more current flowing in a small resistor. So you have a different current basically. The current here is, again, remember, current is the amount of electrons that flows in a second. Okay, so this has a higher current, the medium current, and the lowest, okay, the smallest current. So when you talk about series, the current is basically the same. Even if you do this 0, you still have 83, still moving this way, right? If you make it 120, it's still the same. What the electrons that flow, the number of electrons that flows here is basically the same. All right, but the voltage is different. You know, the voltage across each resistor is different. See? 20.3, so it's different. Now, this is true. I is different across each resistor when it's parallel. Voltage is the same when you talk about parallel connections, and in series we have similar different. Now let's try to think about this. Okay, so going back here. Now in the series, so let's reduce this to practically smaller values. Okay, 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 we're good. Now it's 52. It's 52, 43, and 17. Okay. So our resistance is 52 ohms, 43 and 17. 43 and 17 ohms. Okay. Now the voltage is okay. Okay, what's similar to them is the current. Okay. Let's put an ammeter here. So remove this one, put an ammeter here. Okay, so the current that flows is 0.45. So since this is a series connection, we have the same current across each resistor. Now it's time for us to determine the voltage and the power. Okay, so remember, I is equals to V over R. So when we talk about voltage, our formula is V is equals to IR. So current times resistance, current is 0.45 times 52. So this is 23.4 volts. Okay, and 0.45 times 43. So we have 19.35. We have 0.45 times 17. We have 7.65. Sorry, 7.65. Okay, let's check this out. So when we see a 52 ohm resistor, let's see the voltage. 52 ohms. Okay, so it's 23.21 here. I don't know why is that. Probably due to this. It's not giving us a very huge number. So the ammeter provided here gave us 0.45. Okay, now what if we don't have an ammeter? Okay, so let's remove this one. What if we don't have an ammeter? Okay, the first thing that you're going to do is to make this circuit into one resistor. Okay, so that's 52, 43, and 17. So we have 52 plus 17 plus 43, so we have 107. So this is 107 ohms. 107 ohms. Okay, so this is 107 ohms. So 52, oh, sorry. 52 plus 17 plus 43. Sorry, it's 112. Okay, so it's 112 ohms. Alright, so let's check. Let's try and check. Okay, so so our current, our voltage is 50 volts, and our resistor total is 112 ohms. So this is 50 divided by 112. So actually we have 0.4464 amps. Okay, so this is already rounded up. This is already rounded up. That's why we don't have an exact same value. Okay, but I rely on this more than the more than the ammeter given here. Okay, so alright, so that's what we do. Okay, so basically you have the same current that flows here. So you connect an ammeter here. So see, wait, not 50, not 12, make it 50. Alright, so you have the same current as you can see. So 0.45, 0.45. So that's the trick. Okay, what if you don't have an ammeter? So that's what you do. So you combine them. So you combine the resistors in series, and then do the Ohm's law, I is equals to V over R. You get the total amount of current that flows. Okay, so I'm going to delete this one. This is not really true. Okay, so this is answer times 52. So this is 23.21 volts. Zero point 4464 amps, 0.4464 amps, 0.4464 amps. Okay, times 43, we have 19.1952 volts. 17, we have 17, we have 7.588 volts. Okay, let's try and check using a voltmeter here. So the voltage across the 52 ohm resistor okay, is 23.21. Okay, so we got it. How about across the 43 ohm resistor? We have 19.12 or 19.20. So we have 19.1952 here. So what about across the 17 ohm resistor? We have 7.59. So see, 7.588. So okay. So remember, so the current that we got here is basically I is equals to the voltage total divided by the R total, and the resistance, obviously they're the same. So the resistance total here is 112 ohms. Okay, so how about the power? Now, as what I told you, okay, so this, since they have different resistance and different currents, they have different powers. However, if you're going to combine them, you practically have the same thing here. Now, let's try. I'll use a simplified here. So the power is given in terms of Joule's law. So a while ago we talked about Ohm's law. Now we're talking about Joule's law. Okay, so this. Oh, sorry. Now we have Joule's law. Now Joule's law is like this. Joule's law talks about more about energy and power. Okay, so that's Joule. Okay, so did you know that a kilowatt, or in watts, watt is actually joule per second. So this amount of energy that flows through a second, and that's actually a watt. Okay, a watt? No. Okay, so going back here, what's the formula? Okay, so the formula for power is I squared R, or V squared over R, and or that's also equivalent to IV. Okay, so you can pick whatever of the three, or which of the three. It's don't really matter. But if you're going to be more specific, or you're going to ask yourself, what's the point for each formula? What's the difference for each formula? Well, they have different applications. So you're going to use this if you're going to talk about heat losses. When we talk about losses due to heat, because remember, everything that has a resistance prevents current, or prevents electrons from moving. And whenever you, for example, if you're going to push something, if you're going to exert push, if you're going to squeeze something, you're going to have more force, and you practically make it hot. So friction is one of the reasons why. So more resistance, more losses, and more losses, remember, leads to more heat, and more heat, yeah, more losses. So this is what I squared R is all about. Losses due to heat. So these are the power losses due to heat. But in this case, for our experiment, you can actually use the same formula. It's really not a big deal. Okay. So I squared R, V squared over R, or IV. Okay. Now that we have a current here and a resistance, and we have a voltage, we can calculate for the power. So it's up to you, whatever formula you're going to use. So if you're going to use P is equals to IV, it's okay, or I squared R, it's okay, or V squared over R, it's okay. It's basically the same. Now let's try VI. Okay, so 0.4464 times voltage. Okay, let's try P is equals to IV. Okay, so that's times 23.21. So we have 10.36. Okay, the unit is watts. Okay, it's watts. So how about this one? 0.4464 times 19.1952. So this is 8.5687 watts. And lastly, 64 times 7.588. So this is 3.3873 watts. Okay, so the total, what's gonna be the total? The total power. Okay, so we have 112 ohms here for the total. We have 23.21 plus 19.1952 plus 7.588. So this is 49.9932 volts. And for the current, if I have the same, no, we're not going to total them because the current in a series circuit is the same. So you have the same current. Not really X though, but the current is the same, 0.4464 amps. How about for the power? So we have 10.36 3.36 plus 8.56, 3.3873. So we have, this is 22.316 watts. This is total power. Okay, let's check this one out. Okay, now we have 112 volt, 112 ohms. Okay, and we already know that the current is, right, so 0.45. Now we can use the another formula, which is I squared R. Now we can use this one. So the I squared is, okay, let's try this one. Okay, so our formula here is I squared R. P is equals to I squared R. So this is 0.45 squared times resistance is 112. Okay, so 0.45 squared. Where's the squared here? Squared times 112. Yay! We have power is equals to 22.68 watts. So do we have the same? Not exactly. Don't have the exact same answer because we already use a voltage here, which is basically rounded up, so it's not exact. Okay, so that's the problem because we're not using an exact value for current and the voltage. That's why we have this. Nonetheless, we can, yeah, it's not really 0.45 though. 0.4464 squared, okay, times 112. Yeah, we have, sorry for this one. Okay, if we're going to stick with our current here, we have the same answer, 22.318. Okay, actually 318, so it's 0.006 difference. So we have an error, but it's okay. So that's it. Now that's it how we compute them. Okay, so let's change things a bit. So let's make. So what if we have a different scenario now? We're going to determine the current that flows here, the voltage across each resistor. Yeah, so this is quite tricky because we are already talking about the combination of a series and a parallel resistors. Now all you need to remember is stick to the rule. When we talk about parallel, the voltage is similar and the current is not similar. But series, the current is similar, the voltage is not. Okay, so now that we already know the value of the resistor for this one, so it's gonna be combination of 9 and 3. Okay, the question is, sir, how do we simplify this? Okay, so the trick is to look at the outermost resistor. Now the outermost resistor is 9 ohms. And 9 ohm is the 9 ohm resistor is connected to the 3 ohm. So this is a parallel one. So how do we do this? So basically we have R1, 2. Let's say this is 1, this is 1, this is 2, and this is 3. R3, R2, and R1. Let's say. So combination of R1 and R2 is a parallel one. So 1 over 3 plus 1 over 9. So R12 is, let's use the calculator here. Okay, 1/3 plus 1 over 9. So this is 4 over 9. So 1 over 4 over 9. And this is 9 divided by 4. And this is 0.4. Yeah, 0.444. So ohms. So that's in ohms. So we now know that the combination of these three resistors is 0.44. Okay, so this is 0.44 ohms. Okay, so let's say we would like to determine the current that flows through the 9 ohm resistor. So this is since this is parallel, it's gonna be different. Now, you have to remember the rule. Your current is different in parallel, but the voltage is similar. So, in order for us to determine the value of the current that flows through the 9 ohm resistor, we simply use the Ohm's law. I over R, V over R. So we already know that the current, that the voltage is unknown to us, but we all know that the resistance is 9. Okay, so now, this is a bit tricky. We're going to determine the voltage that flows in this uh, loop. Okay, in this loop. This is tricky because, as we already know, the voltage across each resistor is different, and it is in series. So, how do we determine? How do we determine this one? Okay, so now that we already simplified these two resistors, we can say that 12 volts connected to a 6 ohm and then connected to 0.44 0.44. Right. Okay, sorry, I made a mistake here. So why did it give me ah, this is 2.25. This is 2.25. Okay, sorry about that one. So connected to 2.25 ohms. Okay. Okay. Okay, so the current obviously is the same, but the voltage is different because we have basically series. Now, but we both know that the total voltage is 12. So we have to determine the current that flows through here. Okay, so what's the current that flows through 2.25 and 6? So basically we have I is equals to the voltage total, which is 12 divided by the total resistance. So the total resistance is obviously 6 plus 2.25. 6 plus 2.25 is 8.25. So 12 divided by 8.25 is equivalent 1.45 ampere. So the same current flows through 2.25 and 6. Now, we already know that the current is 1.4545. Obviously, we can find the voltage that flows to 2.25 ohm resistor. So the voltage can be given or can be found or can be calculated using IR. So V is equals to IR. And the current that flows, we already know, is 1.4545 multiplied by resistance, which is 2.25. So the current, or the voltage rather, 1.4545 times 2.25. So the voltage is 3.272625 volts. Okay, delete. Alright, now we already know that the voltage across this is 3.272625 volts. Okay, we already know that one. So, we already know the value of the voltage here. And this is 3.272625. And I is 3.25, 2.272625 divided by 9. So this is 0.36. 36, 25. So that's the current that flows through at this point. and the current is 1.4545 here. So the current here is 1.4545, and the current that flows through here is 0.363625 amps. Now let's check. Alright, so this is the trickiest part. Hope I'm not wrong. Oh, sorry. It's correct! Okay. I'm surprised it's correct. I'm just kidding. See? So, we have 1.45 here and we have 0.36A here. Now, as I already told you, this is a bit tricky because we combine two different we have series and parallel at the same circuit. So all you need to remember is Ohm's law. Okay, I is equals to V over R, and you have to remember that the difference between current and the voltage when it is series and it's parallel. So that's all you need to do in circuit analysis.